Okay, operations in arithmetic in C. So we have the data, we have all the representations. Now we get to do stuff with it. So what is the stuff we're going to do with it? We're going to cover the bitwise Boolean operators, the logical operators, and the arithmetic operations. We'll start with the bitwise the Boolean bitwise operators, and they're based on Boolean algebra. And so this is an algebraic representation of logic. So the states are either true, which is encoded as a bit of 1, and false, which is 0. And the specific operators are the AND, the OR, the NOT, and the exclusive OR. And we represent how these operators work using a truth table. So here is the AND operator. The one operator is on the left, and then the other operand is on the top. And so when you have 0 bitwise with 0, you get 0. 0 bitwise with 1 is 0, etc. So that's how you read these tables. And so for the AND, A and B is 1 when only both A and B are 1. A or B is 1 when either A or B is 1. And so you see for the OR operator, you see this pattern. For the AND operator, it's only when both are 1. Okay? The NOT is just flipping the bit. And this is a single operand operator. So when you see the tilde, you're basically flipping the bit. And then the exclusive OR, A XOR B is 1 when either A is 1 or B is 1, but not both. Okay? So when they're different, A XOR B is 1. When they're the same, they're 0. Okay. So you can apply these across any integral data type. So you can have a long, an int, a short, or a char. And the way this operator will work is to go bitwise through the data type, and then to do that bitwise operator bit by bit. That's basically how it works. So you view these arguments as bit vectors. So here are, basically we're doing characters here. And then you apply that operation bitwise. So this is an AND operation with these 2 bytes. And then you go from right to left or left to right, however you like, and you do the bitwise operator. So again, 1 and 1 is 1, 0 and 0 is 0. Anything with a 0 in the column turns into 0, and this is 1. So that's this operation. So if you have these 2 characters, one character has this bit pattern, the other character has this, that's the result you'll get. The same thing with the bitwise OR. Anytime you have a column with a 1 in it, you get a 1 as a result. The exclusive OR, anytime you have bits that are different, you'll get a 1. Anytime they're the same, you'll get a 0. So you get that. Scan it and validate that it makes sense. And then the last one is the bitwise complement, the tilde, and that just flips all the bits. Yeah.
So good comparison. Is that the final bit pattern that's matching whatever it is? Like 0, 1, 0, 0, 1. Is it whatever you send to it? Like a string or something like that?
When you want to compare values, there's different ways you can compare values. We'll talk about this a little later, but it's basically, you can use a subtractor. You subtract the 2 things. You can use a, I guess it depends on the context. Okay, so I'm going to have you do this, this practice problem. Here are 2 bytes, hex 69 and hex 55. I want you to do this operator on these bytes, all 4 different operators on these bytes. Yeah. What's it? All right, we will start with the first one. 69 is 0110 1001. 55 is 0101 0101. You go bitwise on the AND, and you see that only this one and this one will be set. And this is hex 41. x1 is the exclusive OR. It's the exact same value. But yeah, you'll see everywhere where they're the same, it's 0, and when they're different, they're 1. Hex 3C. The bitwise OR, everywhere where there's a 1 in the column, you get a 1, and then the only places that are 0 are when both bits are 0. X7D. And then the bitwise complement of 55 just flips it to 1010, which is AA. Yep.
Why would you want to do
The actual application of this it depends, but you'll see the exclusive OR being used to test whether this thing is 0 or non-zero. Because if you exclusive OR yourself, the only time you get a 0 is if you are 0. That's one of the ways to do exclusive OR. The other thing with exclusive OR is if you exclusive OR anything with a string of all 1s, you get the bitwise complement. So maybe if you want to flip the least significant byte, like flip the bits of the least significant byte, you would do an XOR of hex FF with that byte. In fact, we'll actually get to some of these examples. Yeah, and then bit masking, the logical AND with a bit mask, say if I do a bitwise AND of hex FF, that means I'm masking out the most significant bits of that value. And this is going to come into play with your program, right? Because you want to mask out just the fraction bits or just the exponent bits. So you're going to be doing some shifting and masking for that, for the AND. Yeah. Yes?
My favorite one is with the exclusive OR, you can swap two numbers without needing the third register. So if you do A XOR B, B XOR A XOR B, you end up with them swapped.
Yes. Yeah. So that's a trick. Yeah.
So you can create a mask to give XOR to other bits.
You can use XOR to do an in-place swap where, yeah.
Or you want to swap like 2 bits out of the byte. If you want to flip those bits, then you can use one as your XOR value.
Yeah, you could do, just set those 2 bits as 1 and then XOR it with that. And then you would flip the other ones, yeah. Okay. The other operation that you're going to need for your program is the shift operation. In C, the syntax is the double less than or the double greater than. The double less than, the semantic of this says take your bit vector x, or your basically your integer x, and shift it left y positions. So the semantic is if you have any extra bits on the left of x, as you're shifting in from the right, those bits get thrown off, dropped. So with this operation, you're always going to fill in from the right with zeros. So if your argument here is 0110, 0010, and you shift it left by 3 positions, you will get rid of the most significant 3 bits, and then you will add 3 zeros onto the other side. So this is shifting those bits, and you get rid of these 3 bits on the top, and then you add those 3 zeros from the right side. Okay? With the right shift, this says take your integer x and shift it to the right y positions. And in this case, you're throwing away the bits on the right. Okay? There are 2 kinds of right shifts, though. Because there are 2 kinds of integers, and because we need to do sign sort of extension kind of stuff with different sized integers, signed integers. So with a unsigned integer, you typically, when you see this notation, you're going to do a logical shift right. And the idea here is that you're going to fill in zeros from the left-hand side. If you have a signed integer x, then you're going to do an arithmetic shift. And in this case, you're going to shift in the most significant bit from the left. And this way, when you have a 2's complement number and you shift it right by 1 bit, this is like dividing by 2, as we'll see. And then because you're shifting in the sign bit, it'll still have the proper sign. Okay. So here is the logical right shift and the arithmetic right shift using this argument. So again, this is a byte whose most significant bit is 1. And if you're doing a logical shift right, so you're basically doing a shift right on an unsigned value x, you're going to get rid of the right 2 bits. Those are going to shift off the end. And then you're going to shift in zeros from the left. The arithmetic one, you're going to start with the same thing. And then because the sign bit was 1, the most significant 2 bits are 1. You shifted in ones there. Right?
How do you force an arithmetic shift in C?
You have to cast your number into a signed number and then do that shift. He wants to, wait, what?
Force the arithmetic shift.
Force the arithmetic shift. So the arithmetic shift is the signed shift.
Is it kind of like in C++ where you can actually call a specific operator instead of doing that?
It's sort of like operator overloading. Your
Yeah.
right, your double rights mean something else based on the type.
Yeah, okay.
Sort of like that. Yeah.
And they don't have a specific name, so you have to actually cast it to a specific thing and then do it. There's no other way to explicitly call that without using a function.
Without using a function. No, you have to just manually cast the data type. It's
Yeah.
done, but the compiler is looking at the data type. Whereas I think with C++, the operator overloading, it just depends on the runtime type of the object. So that's done completely different mechanism for that thing. Yeah.
So what's the size again? Which one?
What's the sign? So the arithmetic shift shifts in the sign from the left.
No, I'm saying what's the size which shift happens? The logical or the
Oh, the whether or not your data type is signed or unsigned. So that's really the only way. So if you're going to use your right shift to divide by 2, if it's an unsigned number, well, the way you divide by 2 is pushing zeros in. If you have a signed number, the way you divide by 2 is actually to push the sign bit in. And we'll see this as an example in the next couple of slides, where that's how you divide by 2. Okay, so here is a practice problem. And I only want you to do the bottom 2 rows. I want you to calculate the number x shifted left by 3 and then right by 2. Well, no. X shifted left by 3 and then calculate x shifted right by 2, both logical and arithmetic, and then do the same for hex 55. So start with this hex CC for each one of these 3. And start with hex 55 for each one of these 3, and then do the operation. Okay. So for hex CC, shifting it left by 3, you should get hex 60. And then shifting it logically to the right by 2, you get 33. And with the arithmetic, you get F3, because you're shifting in the 1 bit from the... With hex 55, when you shift it left by 3, you'll get A8. And then shifting it right by 2, it's the same for logical and arithmetic because the sign bit is 0. And you get hex 15. Yeah, the sign bit is 0. So hex 55 is 0101, 0101. And so for the logical, you're always shifting in 0. For the arithmetic, you're shifting in the sign bit, and the sign bit is 0. Yeah. So someone was asking about in their homework, what kind of shifting do you want to do? Personally, I would shift in, I would try and make them unsigned ints, shift in zeros, because I don't think there's anywhere in the floating point format that you would want to hit. There is no negative number. There is no 2's complement number in the floating point anywhere, so it just makes no sense to have a arithmetic
Some
ratio.
defined.
So especially if you're just operating on raw bits and bit masking, you typically would want to do those as an unsigned shift. Okay. The next set of operators are, so we're done with the bitwise Boolean ones. The next set are just the logic operations in C. And these operations always return true or false. So you have comparison operators, and these are the ones that are used in your conditional, like your loops and your if statements. So greater than or equal to, less than or equal to, the equality check and the inequality check. You also have the logical operators. So if you have conjunctions or disjunctions of these comparisons, then the way you sort of join them together is with the logical and the logical or. And these are different than the bitwise or and the bitwise and, which is why there's two of these things in a row. And the logical not. So you saw the bitwise not was tilde. The logical not is the exclamation point. It's really important to get these things straight because they mean completely different things inside your program when you write them. So, okay. So, some examples. Here you have a character, data type, and you do a logical not of hex 41. And so in C, anything not 0 is considered true, and 0 is the only code point that is false. So here it says not hex 41. This is treated as true, so not true is false. So it return 0. Here, not 0. If you do a not false, then this will return true, which the compiler will make that 1, which is its default value for true. If you do this, do a not of hex 41. This is not true. So this ends up being true. You flip this to a false, and then you flip the false back into the true. Or optimized out, yeah.
But if it's optimized out, that'll actually change what the answer should be.
Uh,
Because if you optimize out the not, then it's 41. If you keep the not in there, then it's 0, 1.
Here's the thing with the compiler. The compiler
Doesn't
is
know.
not allowed to impact correctness. So if it is the case that it's not going to produce equivalent code, it can't make that optimization. And we'll see other places where it's not allowed to impact correctness when we talk about performance optimizations later on. But that's what it does. Okay, so we calculated the value of hex 69 bitwise ORed with hex 55 earlier. What is the value of hex 69 logically ORed with hex 55? Yeah, it's 1. It's true. So you got to know that. So, when you are choosing the OR operator, you have to know, am I doing a logical operation or a bitwise operation? You see this operation a lot. For a pointer, P, what does this expression do?
Make sure the pointer is null and the data is 0.
Yeah, it makes sure this pointer is not null before dereferencing that thing. So that's an easy check, because you could easily do if P is equal to 0 and then do something else. You could actually encode that in your program as long form. But this is a short form of saying, don't follow this pointer if it's null. So it's a sanity check.
That to do with the way we
Yes, it goes from left to right. Yes, that's basically the evaluation. Okay, did I go through this example already? No. Well, here is where the bitwise OR and the logical and the bitwise OR and the logical equality and the assignment operator, not mixing those up is big. Because in 2003, someone tried to slip into the Linux distribution this really interesting backdoor.
Oh, yeah.
So this is something that you're checking for equality. This isn't a system call. And it says, check to see if your options are set and if you are the root administrator. And if so, return this value. So instead of being a double equals, somebody had deleted one of the equal signs and then uploaded this source code. And so basically what happens is if you call this system call with these options, you get your UID set to 0.
Which is the root.
Which is the root administrator account on all the Linux systems. So here is where if you are not carefully auditing your code and someone does this, this is hard to catch, right? With your pattern matcher. Like you're like, oh, there's equal signs here and there, but this, yeah, this is not good. So that was in 2003.
It's easier if you look at other people's code a lot because you get really used to seeing double equals instead of parentheses, but you never see double equals, or you don't see single equals normally inside.
Not usually, but one of the things is we saw earlier is that in C the assignment is an expression, and it returns the result of the expression. So that is a case where people do that. They put the assignment inside the conditional check. So then it becomes, well, let me check the semantic of that assignment inside that conditional, which is basically what you'd have to do here. So this is not necessarily an uncommon thing, but because this is UID and it's being set to 0, yeah, that's definitely not kosher. But you have to know that. Yeah.
Would that always evaluate the false then?
Yeah. It would always evaluate but it would only ever get to this if you had set these options on the system call. So the system call has some options. So if you were the bad guy and knew about this, then what you would do is you would write a program. Say you have an account on the system. This is called privilege escalation. You have an account on the system. You know the system call that you injected your backdoor into. You just write a C program to call that call with these options, and then poof, you're root. Yeah, interesting backdoor. So don't mix up your bitwise and your logical operations is the moral of the story. All right. So I want to get you practice using both the bitwise and the logical operations because I think you're going to need it for your program and for the exam. So if you have two integers, x and y, so these are your two values, for any processor independent of the size of an integer, write C expressions without any equal signs that are true if any of these conditions are true. So we'll start with the first one. You want to return true if x and y have any non-zero bits in common in their low order byte. So if they in their low order byte, first of all, you want to mask off all of the high order bytes of both x and y, and then you want to look and see if they have any bits that are shared, bits in common that are set in the low byte. Yeah. So that's what that parses into. Yeah. Low order byte. So this is what we had talked about before when we talked about endian. Low order bytes are the least significant ones. They're on the very end of the integer. So like hex, I think I had hex 01, 02, 03, 04. That 04 is that least significant byte. Yeah. All right. Think about that. Can you come up with an expression? And I'll take the first answer. First person who answers, I'll go and show the answers. Who can do this one?
Bitwise and?
Uh-huh. But not just a bitwise and. You can do a shift left. So a bitwise and is fine, but this will also get you the bits that they share in the high order bytes too. Yes. So this is where your bit masking is, right? So you are only interested in that low order byte. So this is a way to mask off just the low order byte of this result. So x and bitwise ended with y, and then because you're only interested in the low order byte, you mask that off, and this will return true if bits are shared in the low order byte. Okay. The next one. X has any 1 bits at higher positions than the low order 8 bits. So you're taking your variable x and you're looking at the high order bytes, and anytime there's a 1 bit in there, you want to return true. You have to completely ignore the low order byte though. How would you do that? There's many ways you can do this one.
XOR
Yeah,
value.
you could right shift how many positions? Yeah.
And not 0FF.
So you could do a hex, X and not 0FF. Yep, you could do that. Because when you do a bitwise not of 0FF, you're basically setting the low order byte to zeros. The rest are all ones, and then you're doing a bitwise and. So that masks off the low order byte. So that would be, so this was the first one. Shift this right by 8, and then the low order 8 bits get lopped off. And this is assuming, oh yeah, so this works. It doesn't matter if it's signed or unsigned. You just get rid of the last 8 bits by shifting it. This is the other solution. You take the bitwise and of hex FF, and then the low order byte is 0, but everything else is 1, and then you do a bitwise and with X, and this is exactly what you want. Or you could do this mask, and then exclusive OR it with X. This is trickier, but that's also.
Does not bind harder than and? Order of operations for the bitwise.
Yeah, we'll get to that. Yeah, but yes. Otherwise, there's a mistake there. In fact, remember this, because when I get to the order of operations, if it doesn't show up to be correct, then actually that's a mistake. I believe the bitwise and.
It makes sense because logically not is supposed to bind.
Yeah, because
I think so. We see there's like 15 levels of precedence, so it's hard to remember. This is another well, it's actually any language actually has got this precedence problem. Okay. So X is 0, so return true if X is 0.
XOR FF.
XOR FF.
X and 0.
Oh, not.
If not X.
Oh.
How about if X is equal to Y? Not X XOR, yeah. So X XOR Y, and then the not of that. Think about that. How does that work?
Well, the equal to each other, then the exclusive OR means they're all equal, so there's always going to be full ones, that's going to be true, so that's going to be false then. So there's not.
Yeah, so X XOR Y, if they're both the same, this is going to return 0. And then you want that to return true, so that you take the logical not.
So that would be a good way to obfuscate your code, right?
Yes. We'll talk about obfuscation. No, we won't talk about obfuscation. Take my malware class and we'll talk about obfuscation. Because yes, you could obfuscate C and actually any program. All right, arithmetic operations, signed and unsigned, addition and subtraction, multiplication and division. Unsigned addition. Suppose we have a computer with 4-bit words. What is the unsigned value of 7 plus 7? Well, it's 14, right? You do the bitwise addition, you can do the carries, it's 14. What about 9 plus 9? Yeah, you get that overflow, and then it gets truncated. So, in fact, you'll get rid of that most significant bit, and it turns out 9 plus 9 is 2. So, with W bits, unsigned addition is implicitly modulo 2 to 2 to the W. All of those most significant bits, they just get dropped off, and you get the modulus. So you have to know that. That's what the overflow condition is for unsigned integers. Right? All those bits beyond W are discarded. So what's the value of hex C0000 and hex 7004444?
Oh, that's 1, isn't it?
C plus 7. Oh, so C is 12 plus 7. That makes it 19.
Oh.
But that's an overflow, so you get rid of the 16 from the 19, and that's 3. So 3004444.
Oh yeah, it doesn't round off to the next.
So
It
that,
just cuts off.
yeah, you know, when you add the low parts, it doesn't carry over. It's only at the top that it carries over, and then C plus 7, it turns out, is 1, 3 in hex. Take out, you lop off the top, and then you get this. Okay? So modulo 2 to the W. So that's unsigned. 2's complement is a little different. So 2's complement numbers have a range of negative 2 to the W minus 1 to 2 to the W minus 1. When you add them together, you could get numbers up to 2 to the W minus 2 and negative 2 to the W. So the thing is that both the signed and the unsigned addition uses the exact same adder, right? And you get the exact same result in terms of bits, but when they're interpreted, obviously you get some craziness when you get the overflow. So with unsigned addition, you get this modulo 2 to the W, but for signed addition, you don't get that. In fact, what you get are multiple kinds of cases. Yeah.
So in the last slide, why is the range for like why did we go from 2W minus 1 to 8W?
So you're adding these two together. So that's why. So the potential range doubles, right? Like if you have two large positive numbers, you'll potentially get up to 2 to the W minus 2. Like if you had two numbers that were 2 to the W minus 1, and you add them together, you get to 2 to the W minus 2. So that's like, you know, symbolically, that's your range, but not in the actual representation, because the representation is, this is a W plus 1 bit representation that we're talking about here, but because you're truncating, you get something crazy. That's what, and the crazy is right here. These are the cases that you have to look at. So if it's the case, so here is your symbolic representation. Your number ranges go from negative 2 to the W minus 1 to 2 to the W minus 1. If you have two numbers, two positive numbers, and you overflow the bit position, the bit representation to be in between 2 to the W minus 1 to 2 to the W, it turns out when you have positive overflow, you're going to get rid of that most significant bit, and you're going to turn a large positive number into a large negative number because of the way the overflow happens. Likewise, if you have two numbers that add up to a large negative number, you're going to get rid of that sign bit, and it's going to turn into a large positive number. These are the overflow conditions for 2's complement arithmetic. The easiest way to show this to you is with examples. So here is the case 1. You have, this is a 4-bit number representation. So you have negative 8, which is, so this is negative 8, 4, 2, 1 is the 2's complement version of this. So you have negative 8, and you have negative 5. Negative 5 is negative 8 plus 3. You add these two things together. The 5-bit representation of this is 10011. You want this to be negative 13, right? Negative 16 plus 2 plus 1 is negative 13, which is exactly what you want if you had enough bits. But because you don't have enough bits, you get rid of that bit, and now you're at positive 3. This is the negative overflow, turning your negative sum into a positive number. Likewise, here you have two positive numbers, 5 plus 5. You add them together, you get 1010, and you want this to be 10. And if it were a 5-bit representation where you had that extra bit out here, which would be 0, you would get 10. But you don't. You have a 4-bit representation, and because you set that most significant bit, this turns into negative 8 plus 2, which is negative 6. So this is where you get two positive numbers adding up to give you a negative number. So these are where you have to sort of know this. As you're getting to the 2 billion range and the negative 2 billion range with your ints, you have to know that. For a character, as you're getting to 128, which we saw last class, danger, right? You have a signed character that's reaching towards 128, you better know that might overflow and then wrap around, yeah.
So for case 4, you mean either the truncated, the sign bit is
Yes.
still...
Yes. So the overflow on the positive case means that you're overflowing into the sign bit. Yeah. Whereas the overflow in the negative case is because you truncate that thing, that sign bit. That was the thing you needed. So yeah, that is.
Is this the same modulus with the bias? Is that what it's like?
Modulus with the
We
bias.
Take 127 and add 1 to it, and we get negative 128.
Yes, same thing. You take a character, it's 127, you add 1 to it, and it's all of a sudden negative 128.
Right.
That's exactly it.
So it's got that range minus 1 bias.
At the end, yeah, so the range on the negative side has 1 more than the positive side. Is that what you're getting at?
I mean, normally if it was like 255, you added 1, you overflow, it would become 0, right?
Yeah, so then if you were at negative, if you're
So
at,
if you were to shift that whole property down by a bias of negative 127, you're seeing the same
Mhm.
thing happen. So
things
I mean, negative 128. So you have like, so instead of shifting from 256 on an integer down to 0, then you'd be shifting from sign, it would be from 127 to negative 128, which is the other end of the range.
Let me take that offline. That's a lot to parse.
Okay.
Actually, I'm going to show you a picture that might answer your question.
Okay.
Let's see here. Let me see here. I don't have a picture that shows this, actually. Rats. Thought I had a picture, but I don't. And this is the best picture I have, where as soon as you get down towards here and you keep on going down, you end up wrapping around to the positive side. That's all I have, unfortunately. All right. The next thing I want to cover is pointer arithmetic. Pointers are always unsigned. So you're always going to use unsigned comparisons and unsigned operators with pointers. Moreover, whenever you do arithmetic on pointers, you do the arithmetic based on the type that it's pointing to. So if you are an integer pointer and you add 1 to that integer pointer, you're actually adding 4 to its value, its address. And this is because of the way you're trying to use pointers to index into arrays. And we saw this earlier. So let me go through this example. You have CP is 100, IP is 200, FP is 300, DP is 400, and this integer I is 500. After you increment by 1, all of these values, you get 101 for the character pointer because the byte is size 1 byte. IP++ gives you 204 because it's 4-byte integer. FP++ is 304 because it's a 4-byte float. DP++ gives you 408, it's an 8-byte double. And then when you do I++, this just adds 1. This is your regular integer addition. Okay, so I wanted to show you that.
So if you wanted to look at a byte in the middle of the data type, then you have to cast that to like an integer or double depending on the size of the pointer.
You could if you wanted to stay in pointer land, but typically what you would do is if you have something within a structure that was a byte-oriented thing and the things around it were, maybe you had an array of doubles in the other, you would actually directly access that member, and then the compiler is going to figure out a better way of generating a pointer to that range. So let's see how am I doing on time. 2 minutes, eh?
So in 32-bit systems, why was there a difference between a long and an integer when they're both the same size for 32-bit?
So the long got introduced for the reason of the 64-bitness of this. Yeah. That's sort of where it was used. Yeah.
Can you explain the pointer
The
IP and time?
So this is actually an integer. This is not a pointer. So when you increment an integer, you're getting standard addition, not non-pointer addition. Okay. The only thing I want to talk about with the multiplication is that it overflows just like the addition. So that's all. That's basically it. And then multiplication by powers of 2, you can do this with bit shifting, just because of the way your number systems are. This is like multiplying by powers of 10. You know, you add zeros from the one side or the other. And then these are just cases. Yeah, all right. I don't need to show you those. You have everything for your program, and I might record this and make it a screencast later. The rest of the stuff. All right.